All right. Grade 12 IB chemistry class, standard level, higher level. So it's a John Mac again, and sorry it's been a while since I've seen you. But now we are finally finishing up topic 11.3 in your IB chemistry curriculum and in your textbook. Hopefully you read topic 11.3 already and went back to review mass spectroscopy and also the IR spectroscopy. So the last one you need to know, it will be based off not nitrogen, God, nuclear magnetic resonance spectroscopy, right? The NMR. So this one I find to be probably one of the more standard techniques of the three. That is, if you're going to be, I think, a pharmacist someday, or an analytical chemist, or even a medical doctor or medical technician, you would probably be using this NMR technique the most. Now, at first, it's a little harder to learn. It's a little bit more difficult to go through this. It's kind of a steep learning curve. There's a lot of details to it. But once you get past the details, it's actually pretty good. It's actually very useful, okay? So that's one thing I really like about NMR. Like there's an art to this particular technique compared to the other two that you already learned, all right? So anyways, we'll get started with the NMR. Just get a little background information on it first. Let me share my screen, that would help. Okie dokie. Now let's go to, right, now let's look at this first. I want to go to this beautiful. All right, so we are here with the NMR spectroscopy. All right. So we are looking at how does NMR work. So the structure of a molecule can be investigated using the NMR spectroscopy. So basically, nucleons, which are protons and neutrons, have a property called the spin, which can be one of two opposing states. Okay? So in the nucleus, the nucleons with opposing spin will pair up. Again, let's look at that one more time. Nucleons, protons, and neutrons have a property called spin, which can be one of two opposing states. So in the nucleus, the nucleons with opposing spin will pair up. Any nucleus with an odd mass number has an unpaired nucleon and therefore exhibits spin. This generates a small magnetic field and the nucleus behaves like a miniature bar magnet. Let's go back again. Let's take a look. Okay, they're just putting it on the table, no big deal. All right, so now I think we should have a little bit more here. No, I thought they would have some even ones. Okay, the next one will be even numbers. Oh, okay, so then nuclei with even mass numbers, such as oxygen and carbon, do not have a spin. All right, so far we've seen hydrogen and carbon-13, one of the three isotopes of carbon, by the way, and then phosphorus. And then there's also fluorine, I believe, but I can't remember what fluorine's atomic number is right or bad. I don't have my periodic table. Okay, so those are even numbers that do not have spin. The magnetic fields of nuclei with overall spin can be represented by arrows. Normally, they are randomly oriented. As you can see, they're all in different directions. Okay, so the magnetic fields of nuclei with overall spin can be represented by arrows that are kind of pointed in random directions. If the nuclei are exposed to a strong magnetic field, they can align in two ways, okay, with the field. Okay, so that's like with the field here of lower energy level, okay, or they are against or opposed to the field with a higher energy level. And the difference in energy between these two alignments is what we call the energy gap, or delta E here. Now, there will be another diagram that is from your IB chemistry textbook that we'll be looking at in a different PowerPoint later. And that would be more useful to your exam, okay? This is a very generalized diagram here between like the energy levels of your nuclei that are with or against the magnetic field. And the nuclei tend to align with the field because this is the lowest energy configuration. So what we saw here, right, what they're saying is there are more of these lower energy level alignments. Again, so the nuclei tend to align with the field more than against it because that's the lower energy configuration. Now the nuclei can be flipped so they oppose the external magnetic field. That is called excitation. Okay, that requires some energy, an input of energy, and that will be equal to your delta E, or the change in the energy level between the alignments. And that's usually done by radio waves, okay, or radio frequency radiation. Okay, let's take a look at that animation one more time. So they can be flipped, they oppose, that's the radio waves coming in. They flip them and excite them, and that's equal to delta E energy level. And the excited nuclei, okay, will later flip back up so that they are aligned with the field. That will be called relaxation. This results in a release of energy, and that will be equal again to delta E. Again, let's take a look at that. So that nuclei can be flipped, okay, excited back again, I mean flip back up, okay. That's still equal to the original delta E. And as long as radio frequency radio waves continue to supply energy that matches the delta E energy level change, the nuclei will continue to flip alignment back and forth. And then that is what we call the concept of resonance. Again, let's see the animation one more time. So as long as they keep getting radio waves, right, and it's equal to enough energy, then the nuclei will be able to flip back up again. That's resonance. All right, so that's how NMR works. Okay, so what does the NMR spectrum tell us? The different chemical environments, bonds and atoms surrounding a nucleus, affect the strength of a magnetic field that must be applied to a nucleus in order for it to enter the resonance state. So by measuring the strength of a magnetic field that must be applied, NMR spectroscopy gives us information about the local environment of specific atoms in the molecule. This can be used to deduce information about molecular structure. Now, so normally the two, a long time ago, actually in A level, you need to know both of these. But lucky for you guys, for IB chemistry, you only need to know about the environments of the hydrogen atoms used in NMR spectroscopy instead of carbon-13 isotope, all right? So we'll be looking at more at looking at the different environments of like a molecule based on their hydrogen environments. This left diagram here is based on carbon sections or carbon environments, but we don't look at that in IB chemistry. Okay, this is all about the carbon. I'm going to skip over to stuff about hydrogen. All right. Now, okay, just a second. We will get to that a little bit later. I'll come back to this. Let me get to hydrogen, TMES. Sorry. Okay, so let's take a look at then NMR spectroscopy for hydrogen. Okay, and we're using NMR spectroscopy to study hydrogen atoms in a molecule. Right, let's play. So the sample is first dissolved in a solvent. Okay, it is important that the signals from any hydrogen atoms, okay, whatever the tracing and analyzing, so the signals from any hydrogen atoms in the solvent should not swamp over or overwrite the signals from the sample. Okay, that's a very small little pipette tube here. Yeah. Now there is the sample dissolved in solvent, and this would be your nuclear magnetic resonance tube. To avoid this, the solvents without hydrogen can be used. Now, this is the stuff that is kind of in the reading in your textbook on cognitive, and it's not something that you really need to know. It could be a multiple choice paper 1 question about really what they were using here when they're, but really you guys are not really responsible for the specific details of how the machine of NMR works. But this is just some background info for you, okay? This is more like for your information kind of section. So anyways, to avoid that solvent, so you know what the question says, to make sure the signals from hydrogen atoms in the solvent do not swamp the signals you get from the sample overall. So to avoid that, okay, so you use solvents that, okay, so yeah, you use solvents without hydrogen. So usually they use solvents that contain the isotope, like an isotope of hydrogen, that's called deuterium, which has a mass of 2 here, okay? And that will be used, okay? And we usually call that isotope of hydrogen a D, so that we don't have to keep writing 2H, but it's another isotope of your normal hydrogen. So these here, instead of having like a hydrogen or a hydrogen here, okay? So we will be using solvents that will have the isotope of hydrogen, okay? Deuterium. That's what has been put in this here, okay? So each unique hydrogen environment in the sample gives rise to a separate NMR signal. Okay, so for example, ethanol, this is ethanol, remember, an alcohol, contains 3 unique hydrogen environments. So let's go back and look at them again. They would have flashed it very quickly. The first one was red. That's 1 hydrogen environment. The next one is the 2 middle connecting hydrogens here in blue. And the third one is that hydrogen all by itself attached to the OH, right? So again, let's take a look at your 3 hydrogen groups in. So now, when we look at this, we're talking about 3 chemical environments, okay? And they will be very distinct hydrogen regions that will be read by your NMR spectroscopy machine. Okay, so again, I showed you earlier, we have the red hydrogens, the blue, and the green. Now, the HNMR spectrum of ethanol, then because there's 3 distinct regions, the red, blue, and green, then your reading from your machine will read 3 sets of peaks, okay? So now, you don't know this yet because you haven't learned about carbon-13 or the carbon-like NMR spectroscopy. This diagram, by the way, is a high-resolution nuclear magnetic resonance spectroscopy reading. Now, this is something that we'll be looking at later in topic 21. That's for higher level. That's the higher level students chapter or topic in your IB chemistry textbook about the higher level students' understanding of the spectroscopic identification of organic compounds. But for standard level, you 5 students, all right? So that's Chow and Tracy, Ben, Kevin. And then who's the last guy? Who am I missing? That's it, right? Chow, yeah, Ben, Tracy, and Kevin. Chow, Ben, Tracy, and Kevin. I don't know who I'm missing here. I must be like brain dead today. I'm sorry if I missed a name there in your 5. Oh, Pema. Pema, sorry about you, okay? So you 5, you don't have to worry about. Whatever I'm going to talk about, if I show you something, don't mind you, higher level students, you do have to understand these multiple jagged peaks in each set of categories, okay? But again, for standard level, you would see on a low resolution spectroscopy diagram, a single, more like this one, you see more of this single peak rather than a bunch of jagged peaks, because high resolution means you can see more detail into how you split the hydrogens within your molecule. So in your like low resolution spectroscopy, okay, for the standard level students, you would only see like just one big blobby peak rather than the detailed peaks that really show more detail about your hydrogens. Okay, so yeah, anyway, so those are your like groups there. So they're just showing you, again, let's show you one more time. So you can, this is kind of where you will go to later in topic 21. The blue was here, red was here, was, okay, so if you didn't see it, look carefully. There's your blue, okay, your middle hydrogens, that's your terminal hydrogen attached to the OH group. And then there's your red hydrogens, terminal hydrogen as well, of the CH3 on the other end of the molecule, okay? Yeah, so anyways, for those who are in like the higher level, okay, the signals, unlike, okay, so in topic 11.3 for standard level, as you saw in your cognitive textbook, you would not see these kind of multiple peaks. You would see this in topic 21 for HL. So, but in the high resolution ones, the signals are not single peaks, and that's due to hydrogen atoms in the same environment in different molecules experiencing slightly different magnetic fields. That depends on their adjacent hydrogen atoms, okay? This would be a question, by the way, for paper 1 multiple choice for the higher level students in topic 21, okay? That's a conceptual one for the HL. So we're kind of already looking a little bit at the HL topic 21, but we'll go into that detail a little bit later. Okay, now anyways, the chemical shift, what I mean by shift, okay, is relative to the default signal of 0. Okay, so all of that means absolutely nothing right now until I go back and I explain what that TMS means. There's something called TMS. This is a reference chemical that we will be looking at. Okay, so before we can get to do these problems, let's start from the beginning and go to a different PowerPoint where I'm going to start over into the nitty-gritty details of what you learned from your textbook on cognitive, right? Give me a second here to share a different screen. Oh my God, now I can't even like, where's my share screen? Oh, righty. So we are now on my own made PowerPoint, not the animated ones, okay? And we really took some time to make this one. So mind you, it might be a little bit messy. Okay. So NMR basically is a technique, right? A powerful technique, okay, to determine the structure and arrangement of molecules in particular nuclei with an odd number of protons, like we saw earlier in the animated PowerPoint. So in IB Chem, we only look at the hydrogen-based NMR, and then there are other types. And so, the other one that I forgot to show you in that table is actually the fluorine one with a mass of 19. I'm not sure that's an isotope of fluorine. Maybe it's not. Maybe it's just pure fluorine. Okay. So, anyways, we only care about hydrogen. Okay, so we only care about this one, hydrogen, NMR. Okay. All right. So, anyways, so these type of atoms behave like tiny bar magnets. Okay. So if you apply an external magnetic field, they'll either line up or race against the external magnetic field, as we saw in the animated slide. So, okay. And then let's see. So if you place an external magnetic field, some of the nuclei will line up with an applied field and some will line up against it. Okay. And then that arrangement leads to 2 nuclear energy levels. Okay. So again, like I showed you in the animated PowerPoint, the radio waves can provide the energy needed for the nuclei to reverse their spin and change their orientation or direction in the magnetic field. So, okay, so basically something is placed on an electromagnet and the field strength is varied until the radio waves have the exact frequency needed to make the nuclei flip over and spin in the opposite direction, like you saw in the animated, okay, PPT. Got that? And then that is what we call the resonance. And that can be detected electronically. And then that is what is recorded in your NMR spectroscopy machine. So again, okay, let's go to this diagram here. So this is a different version. That is what you will be more responsible to know, okay, for this one. So again, if you are aligned up with the external magnetic field, you're down here. Okay, this is a low energy spin state. Okay. If you're lined up against the magnetic field, you're then in a high energy, okay, spin state going the opposite direction here, okay? So now what NMR does is that it shoots the radio waves. You saw that, remember, in the animated PowerPoint? So it shoots the radio waves at these nuclei, and that's enough to be able to flip their spin states, okay? And then what it does is determine the energy required, here we go, the energy required to flip those spin states, and then it produces that as an electric signal, which we see as a spectrum in the electromagnetic spectrum. Okay? So here is that energy difference. That is the delta E that we saw earlier in the animated PowerPoint, okay? Anyway, so NMR is a very low energy technique, right, that interacts with the nuclei of atoms, okay? So there is, you know, enough energy in the radio waves to change the spin state of the nuclei, and then that is the energy that is determined, okay? And then we basically look at the energy required to flip that spin state, okay? And that depends on then the environment of the atom. Okay. So if we have an NMR machine, it's very difficult to really compare one to the other, okay? So we use this chemical, okay? And this is what you saw earlier on the animated slide, and they didn't talk about it there. We're talking about it here. This chemical is called TMS, or known as tetramethylsilane, okay? And this would be used as a chemical standard, all right? To standardize your measurements. Here it is. This is your TMS. So this is shown a little bit more spatially arranged, and this is more just a flat 2D version of it, right? So this is your TMS. Now, okay, so basically this TMS, a chemical, okay, we just basically use to zero your machine, okay? And it's not actually involved, it's not a part of the molecule, by the way, that you're analyzing, that you're trying to figure out what the heck it is. So anyways, this TMS, okay, so it produces a single small peak on the NMR diagram. And okay, it would be used as a reference point usually at 0 parts per million, okay, which means 0 chemical shift on the diagram. So basically, it allows us to get a 0 point on an NMR, and then for our target samples that we're interested in analyzing, we work to the left of that peak value. Okay, so let's look at this, okay? So again, TMS as a standard is the reference at 0 ppm. Okay, there's no shift there, right? And so it allows us to get a 0 point on the NMR. And for our target samples, the readings will be all to the left of where TMS is on the diagram, okay? So the NMR diagram is displayed as a series of the peaks. So this is what I'm saying for a standard level. You don't really have the jagged peaks in between. They're just one mountain at a time, okay, rather than multiple mountains. Or yeah, single peaks only on standard level diagrams. For low, this is all low resolution, okay, nuclear magnetic resonance spectroscopy, okay? This is for standard level in topic 11.3. I'm going to repeat that for the last time in case you're all, you know, sleeping on me right now. So anyway, so this one, okay, is a series of peaks that corresponds to the protons, or basically your hydrogens, that are present. Got it? So anyways, all these peaks, sorry, are going to be compared, okay, to the TMS that you saw earlier. So let me go back a little bit. Yeah, so they're all compared to the TMS, and this, wherever they move away from TMS, that is called the chemical shift. And the unit for that is in parts per million, ppm, okay? So this gives us an indication of the type of proton that we could be dealing with in a molecule. So basically, the more to the left of TMS that we are, the more closer you are to an electronegative element. Okay, so more electronegative elements are on the left here. Got it? We're basically, you know, the less the charge density you have as a proton. Okay, sometimes that's also asked on your multiple choice paper 1. So we don't need to know the specific use of the MRI machine, like I told you earlier, the details. Okay, that's all can be very, very like complicated. But we do need to be able to interpret these diagrams that you see here. Okay, you have to interpret the spectrum. Now, the heights of the peaks. Okay, so the height of the peaks, how tall they are. Okay, which is also really telling you about the area of the peak underneath that peak, or the space that occupies how much is inside that peak, right? So anyways, whether you call it the height of the peak or the area of the peak, which is sometimes known as integration, okay, the integrated little peaks, okay? So these tell us how many protons or hydrogen are present in that environment or in that chemical environment. So let's say if this peak is 3 times as big as another peak, that means it has 3 times as many hydrogens as that peak that's smaller. Got it? And usually you would have a scale that you can read on here, you know, 1 to 7, 1 to 10, whatever, 2, 3, 2, 4, 6, 8, whatever. Okay, so that will be in the y-axis here of your diagram. Okay, so let me go back here in a second. Now, so sorry here. I think I already talked about the, let's do this one now. Okay, so the Proton NMR, okay, is used to determine the number of distinct chemical environments there are in a molecule, right? And the number of peaks in an NMR, right, will tell us the number of different hydrogen environments in the molecule, right? So again, in the low resolution NHMR, okay, the number of peaks is equal to the number of different bonding environments experienced by the hydrogen nuclei in the molecule. Now, the complete list is given in data booklet, your IB chemistry data booklet, table 27. That comes after your infrared spectroscopy table, okay? Okay, so here, let's take a look at this diagram. This is before I did my scribble in it. Look at the clean diagram right here. Okay? Here we have propanone. And so here's the structure right here. I kind of wrote it in a very different way. Instead of doing it left to right, we're showing clearly what it kind of looks like in any angle. So if I want to put propanone or run propanone, a sample, through the NMR machine, okay, so let's say this is what we get from the machine. We get 1 peak. So that means we have 1 chemical environment. That's 1 chemical environment. I'm not looking at the TMS, right? That's the standard there. So I got 1 chemical environment, 1 mountain, 1 peak. Okay, so that's 1 chemical environment for the protons or hydrogens. Now, if we have a look at the structure here of propanone, okay, we've got basically 2, okay, my mouse, here we go. We have 2 CH3 groups, 1 here, 1 here. Got it? And they're on either side of this carbon-oxygen double bond. But because both these CH3s are bonded to the same thing, basically the same carbon attachment here, the same carbon environment, then that means that these CH3 groups are actually in the same chemical environment, or basically they're considered, when they're identified by the NMR machine, as a similar or the same chemical environment. Okay, so they're not different in your NMR machine. So in the machine will identify them as 1 peak, but the peak will be a little bit higher here instead of a small peak, because if they're identified, even though they're identified as the same environmental chemical environment, there is a lot of hydrogens in there, right? So there will be a lot of hydrogens. That's why the height is a little bit taller. Make sense? Okay. But anyways, they're the same chemical environment. They're both a CH3 group that's attached to the same carbon double bond oxygen. Often this will occur if we have symmetry. So here we go. If we have symmetry in the molecule, which we do here in propanol, this is something that you typically find. And then we can see that there's a line of symmetry here. Okay, so that means we have half as many pieces as we would expect. Okay, but still, that peak will show the combination of other hydrogens. That's why it's pretty tall. Again, the height of each peak, or also the area under each peak, is proportional to the number of hydrogens in each environment. Okay, next one. Now, this one, let's look at the clean diagram on the left here. Is oh God, I can't even pronounce it. Dimethoxymethane. Okay, dimethoxymethane. Dimethoxymethane. So, okay, this one, on the other hand, unlike propanol, it has now, with the NMR reading, it has two peaks. So that means I have two distinct chemical environments. So in your structure here, we clearly see some CH3s at both ends of the molecule. And then in the middle, I have a CH2. Now the CH3 they're both similarly connected to an oxygen, okay? So even though there's two of them on both ends, they're connected to a similar oxygen, or they're connected to oxygen in a similar fashion, okay? So then, with respect to the NMR machine's reading, the NMR machine will identify them then as chemically equivalent. So they will be identified as the same chemical environment. Now, the CH2 in the middle here is connected to two oxygens. So it's in a very different environment to the CH3s at the end of the molecule. So then the NMR machine will identify this CH2 as a very different peak on the machine, as we see here. Okay? Also, one thing I want you to point out is the CH2, look, it's shifted more to the left than your CH3 at the end of the molecule. And another reason for that is since this CH2 is connected to two oxygens instead of only one oxygen, like each of the CH3s on the end here, okay? Because that CH2 is connected to an additional oxygen or to more oxygens, its chemical environment is more electronegative, which is why it gets detected more left away from that TMS, okay? Since the CH2 would be overall more electronegative than either one of these CH3 groups. Make sense? And anyways, as for the peak height here, okay, so as for the peak height here, you can see that their size, again, indicates the number of hydrogens in each chemical environment. So obviously, the CH2 has less hydrogens, that's why it's shorter peak, and these being the same chemical environment that combines both the left and the right end has more hydrogen, so it has to be taller than that yellow CH2 group, okay? Because the green, okay, peak here means that represents my CH3 group, and there's more hydrogens altogether. Okay, again, the height of each peak is proportional to the number of hydrogens in each chemical environment. Got it? All right. Sorry, let me go back here. Okay, now. All right, so anyways, one of the key things that we need to be able to do, okay, is to determine the number of chemical environments in a molecule, okay? So again, every time there is a different environment, there will be an individual peak produced, right? So each peak is representative of a distinct chemical environment on your NMR spectrum diagram, the graph, right? Okay, so this is some questions now that you are to practice on your own. but I'm just going to go through the answers. But if you want to stop here or pause at these kind of questions and try them on your own, you're more than happy to. This question, basically, you have a number of different types of molecules, okay? And we need to be able to determine how many peaks, right, we would see in the NMR machine, right? So the easiest way is to draw these structures, right, using the principles of organic chemistry, okay, from topic 10. That's why you learned that first before we came to topic 11.3. Okay, I know what I'm doing. Now, anyways, so, you know, these can't just be done blindly, really. Some of them you could, really, but it always helps to actually draw out your structures the way we learned in topic 10, okay? Because it'll make it much easier for us to determine the different chemical environments. Now, mind you, we're still on low resolution NMR spectroscopy, okay? We're not on the higher level yet from topic 21. We're still on topic 11.3, right? And again, the key thing is the number of peaks represents the number of chemical environments. So we're going to start with ethane, okay? Ethane, ethane, how you pronounce it. Okay, formula is CH3, Okay, here we go. Now, with ethane, right? So basically in ethane, we have two CH3 groups, and they are both connected to each other. So the NMR machine would only identify one chemical environment or one peak. There we go. We just say one. If that's all they're looking for on your exam, just say one peak. You might have to explain why, maybe. Depends if you're paper 2 or paper 1. Okay. The next one we're looking at then is going to be propanoic acid with the formula of CH3, CH2, COOH. Okay. Now, when you draw out the molecule, draw out the structure, okay? So, unlike the ethane, okay, this propanoic acid has quite a few different hydrogen groups or hydrogen chemical environments, different protons groups, okay? So, it has a CH3 group, got it? Then it has a CH2 group, and then it has an acid functional group. So the NMR will analyze these chemically distinct proton groups or hydrogen groups, okay? So the easiest one is to recognize right off the bat, okay, is this hydrogen attached to the acid here, got it? So that's an acidic alcohol or acidic OH group, got it? So this is an environment that's all by itself here, so give that color green. There's nothing else similar to it in this molecule. And then we have a middle CH2 group. So, but this CH2 group is also connected to the acid functional group. And then we have on the left a CH3 group in blue here at the end. So then there's this one, the blue, yellow, and green. That's 3 distinct chemical environments. Okay. Next, we will do 2-chlorobutane. So we have, you know, okay, so let's see. We have CH3, CH2, CH, Cl, CH3. Oh, look, we have a halogen. We have a halogen in here. Okay, so let's draw it out. Okay, 2-chlorobutane. CH3, CH2, CH, Cl, CH3. All right, so we have 2 CH3 groups, but they're on different ends here. And then let's ignore them a little bit for now. Okay, and we have a hydrogen connected to a carbon with a chlorine, that's right there. Okay, okay, and then we have just another CH2 group here in this side. So the question we should ask first is, look at the CH3 groups on both ends. Are these CH3 groups the same chemical environment? Well, look at it carefully. One of the CH3 groups is connected to the carbon. So this CH3 group is connected to the carbon with a halogen, with a chlorine. And the other CH3 group here in purple is connected to just a normal CH2 group. So because they're not really connected to similar parts of the molecule, then these two CH3 groups will be considered different chemical environments, okay? So because they're both different and these are their own chemical groups here, or in chemical environments here. So this CH2 is its own chemical environment, and so is this carbon attached to the halogen directly. They're their own separate ones. So these are two peaks here, and these two CH3 groups are not the same chemical environment, so they will have their own peak. So overall total, we will have 4 peaks, or 4 chemical environments on your NMR diagram. Next. Okay, we're looking at but1ene, or 1-butene is really what it is, okay? So let's look at that. Okay, see, this is why if you just have this, that's really not going to tell you anything, right? You're going to have to draw it out. Make sense? All right, so we draw out but1ene, or 1-butene. This is a very crude, like, structural formula. That's not showing the structure. Just, yeah, it's a condensed formula. I'm sorry, condensed formula. Okay. So anyways, but1ene. Now, this is showing you how you could do it, but without having to draw the structure, in case you're running out of time on the exam. Okay, so but1ene, or 1-butene, has a CH2 group at the end, which is attached to really a carbon double bond. Then we have the CH that comes after the double bond, just attached to a hydrogen. Then we have a CH2 group here, another one. Okay, but that doesn't have, this CH2 group does not have a similarity to this one, because this CH2 group in purple doesn't have a connection to the double bond like this CH2 on the end it does. Okay, and then we have a CH3 group at the end here in blue. So again, yellow, green, purple, blue, we have 4 different chemical environments. So therefore, the NMR spectroscopy will show 4 peaks. Okay, now, sorry, let's go back here to but2ene, okay, or 2-butene. Okay, CH3, CH, and then there's a double bond, CH and CH3. Now, this diagram, I just got off the internet for you. Yeah, I showed you quite a few things. There it is again. Now, this one is one of those ones that have an isomer, cis, same side, and trans, opposite side. Okay, so this is the 2 isomers of it, but no matter which one you have, yeah, I mean, let's say, for example, I take the trans one. I could draw it out going from here out here. So this is like C carb connected to 3 hydrogens. Then you go down, move past the chain to the next carbon, single bond. There'll be hydrogen above it. Then this carbon will be connected to the next carbon, the 3rd carbon, with a double bond. And then this carbon would have just a hydrogen below or above it, doesn't really matter here. In this case, it's just below it. It could have been above it, it doesn't matter. And then finally at the terminal, you have a CH3 again at the end, okay? So by looking at this diagram here, okay? So despite having this cis or trans isomer configuration, you basically have 2 similar CH3 groups that are at the ends here, at the terminal ends, okay? And then there are 2 middle hydrogens attached to similar carbons that are both part of the same carbon-carbon double bond. And these CH3s are not different from each other in terms of the chemical environment, okay, representation. Okay, they're both connected to a carbon that is equally connected to the double bond. So there's not any difference between these CH3 groups at the ends. So then there's really only 2 distinct chemical environments here. Okay, so basically one of them would be the CH3, and the other one would just be the hydrogen that's connected to, the carbon double bond. And they're both similar here. So this is one group, and this is the other group, the CH3. So there's 2 peaks here, all right? For 2-butene, but2ene. Okay. All right, so here again, this is something that would totally show up on your IB chemistry test. We have a low resolution NMR diagram, and the chemical formula, this mystery formula, not really mystery because we know what it is now. Okay, so basically we know that we're putting a sample of C2H6O through the machine, and we're going to use this diagram, okay, to determine a possible structure for this molecule. Okay, so okay, now there's two versions of these diagrams that were given to you for standard level. If they give you something like this, okay, so you got your peaks here. They might give you these little ladders that are above the peaks. What they are called, they're called the integration levels. Okay, so the overhead lines that are above your peaks. Okay, that tells you guys the areas to work out. Okay, underneath the peak, to tell you how many protons are in each chemical environment. Okay, so now, okay, to work out what these protons might be, okay, you're going to have to use, again, your IB data booklet, page 27, to see the functional group values. So from that table in your IB data booklet, you see then at between 0.9 to 1 ppm. Okay, so from 0.9, that's this range, to 1 ppm, we generally find your CH3 groups. Okay? Now, because this has 3 hydrogens in it, that's why there's a higher peak here, which is typical for your CH3. Now, okay, we have an oxygen in this molecule, right? There's C2H6O. There's a single oxygen in this molecule. Okay, so we have an oxygen in the molecule. Okay, and we got to decide where it is in the integration here. Okay, so we have an integration that can basically account for that oxygen. Okay, now the alcohols are a little bit tricky here, because it's somewhere on your IB data booklet, the table 27 is like, for an alcohol, it's somewhere between 1 to 5 ppm. And that's kind of a very wide range here, okay, because there could be other peaks in between. Got it? So the main thing is that it really, okay, it only integrates for 1 hydrogen. Okay, so this is most likely to be probably an OH group over here. Okay. Okay, so then the 2 hydrogens, okay, at around like 3.5 on your IB data booklet is typical of a CH2 group. Okay, that could be a CH2 group that is attached to the oxygen, right? So now, okay, some terminology here. Okay, we're gonna call anything at the end. Sorry. So when we talk about something at the end that ends the molecule on either end, we're going to call that a terminator, okay, because it terminates, it stops, okay, it ends the molecule. And then anything in the middle of your molecule, okay, that's not at the end, we'll call it a connector, because I'm kind of sick and tired of just, saying the middle one or whatever. We'll say a connector. That is stuff in the middle. So a connector is something that continues the molecules in the meat of the molecule. So the CH3 group is usually going to be a terminator, and it ends the molecule, it's on one end. And the OH usually would be, in this case, a terminator as well. So we'll put the OH in the other end. And then the CH2 group is usually always in the middle, or the connector. Okay, so that would be somewhere in here. And then we're going to have the CH3 connected to that CH, and then this CH2 is connected to the OH functional group. So this obviously clearly looks like ethanol. Okay, so that's our structure of ethanol. And they might ask you too to name it, so you should know that it's called ethanol. You guys should know how to name your basic organic compounds by now. Okay. All right, next. Here's another problem. So here's an organic compound with the molecule, okay, C3H6O2. Okay, so now look, it looks similar to before, I think. It has 1 additional oxygen. Okay, so here's the NMR spectrum diagram once the machine is run, the sample. And now we're giving this additional information. This is something that you would totally find on your IB test. The organic compound, okay, so okay, we're told that this thing reacts with bases, okay, from remember topic 8. So And it's also, they also say it's soluble, it dissolves in water. So it's soluble in water. So the question that they're asking again, similar to the other one, is using the diagram, you need to draw a possible structure for the C3H6O2, draw the actual structure, the details of it, and give it a name as well, okay? So the best way to approach this is definitely trying to figure out what's going on at peak A, peak B, peak C. Got it? Now this is almost looking like an NMR high resolution spectroscopy, okay? Which you'll be seeing more in topic 21. But then we're going to zoom out a little bit more so that they all look like just single peaks, which is for low resolution, okay? Anyway, so from this information in the palm, if it reacts with a base, most likely it is an acid, okay? Because you learn in organic chemistry that, and in acid-base chapter, okay? So now, in organic chem, okay, when we talk about stuff from topic 10, if you're told that, okay, so, yeah, so from topic 8, if it reacts with a base, it's definitely an acid. In organic chem, though, when I'm thinking of an acid in an organic molecule, I'm thinking of a carboxy functional group, okay? So I'm thinking of more like, in this formula, I'm thinking of like a C double bond O, and also an OH group, okay? So if I look at then this NMR spectrum, we see 3 peaks or 3 chemical environments, okay? One of those is all the way up here to the far left at around 12 ppm, okay? And then we have these 2 other peaks which are closer to each other. Okay, now this diagram doesn't have that ladder above it. We don't have the overhead line called the integration line, okay? So we don't have that above the peak here. But what they did give you instead is telling you directly, like this one, this peak here is telling you how many number of hydrogens are in each chemical environment. So this one indicates I have 1 hydrogen. This one indicates I have 2 hydrogens. This one indicates I have 3 hydrogens. Got it? Anyway, let's look more carefully at the 12 ppm, 12 parts per million peak. So this would usually be typical, okay, more of an OH of an acid, okay? So you can see that from your data booklet, table 27, your IB chemistry data booklet. So I must have at least an acid functional group here. So there we go. CO double bond OH, okay? So I should have at least an acid functional group here. And I would usually, that usually is always going to be a terminal group at the end of the molecule, okay? Then we have the 2 other groups here, the 2 other peaks. We do have a CH, okay? And then we also have a CH3. So the CH3 is usually in the range of like 0.9 to 1 parts per million. So most likely this tallest peak to the far right, the closer one to TMES, okay, is going to be your CH3 group, okay? And that will also be most likely a terminating group, the end of the molecule, okay? Stops the molecule from going on. And then we can look at the 2 hydrogens. Okay, we still have 2 hydrogens at peak B. Got it? That's around like what, 2.5 ppm? So from your data booklet, that is in the range of like a CH2, okay, which is definitely a connector group. So it should be somewhere, in the middle. Okay? And our terminators will be at the end. So you can, put it together on your own, how that will end. So this is like for here, you're going to put a CH2 somewhere, and then you're going to end it somewhere else. So again, I would probably end it like this, a CH3, CH2 in the middle, and then your little acid COOH terminal group is on the other end, okay? So that would be, you can draw it out. You could draw a carbon and the 3 hydrogens sticking out, draw a carbon, 2 hydrogens above it, and here, you draw this part here, okay? You CO double bond, CO single bond to an H. And the name of that then would be propanoic acid, right? It's that 3 main carbons unchained, but it's definitely an acid, so it would be oic acid, okay? Hopefully that's okay for you guys. Nothing new for you, really. Okay. Now, just to go back and really review this one more time, okay? the shift, something that students do have trouble. So without all that mumbo jumbo that you get from the actual NMR spectrum diagram, let's revise this part a little bit, okay? So basically, you know, on your x-axis, you start from 0 ppm all the way to 12 ppm, parts per million, okay? Now, in terms of, for the data booklet table, okay, alcohol is a bit of a problem. The value for alcohol, or the H's on the like ROH range that you see in your IB data booklet, is somewhere between 1 to 5 ppm. And like I said earlier, this is a very, like, you know, too big of a number range, too broad of a number range. So because you, like I said, you could have had some other types of peaks showing up within this 1 to 5 range. So this info is not so useful for you, okay? I mean, to identify, like, you know, what you really got going on here for your spectroscopy, okay? So what I would be recommending, if you can recognize another specific set of basic values and practice identifying how they show up, you're more likely to get your values correct, okay? So the values from your IB data booklet that are more useful for you to be familiar with, maybe even memorize it, even though you have it on your data booklet. We'll start here with the halogens. That's usually a range of between 3 to 5 ppm, approximately, okay? And then you have around your aromatic groups. That's your ring groups, right? Your rings that could be attached to the molecule. They call them aromatics, in case you don't know that name by now. Aromatics are your ring functional groups, or ring-based attachments, and that's around 7 parts per million, 7 ppm. And then, of course, more on the left side, okay, you have basically, you know, you have the terminal hydrogens on a carboxy or aldehyde, okay, that you see here, okay, and that ranges between 9 to 12 ppm, okay? So, I mean, you can analyze the other values that show up on your IB data booklet in table 27, okay? But I think, you know, really the best way for you to remember these, okay, these are some worth memorizing or being familiar with, but really what it comes down to is this, okay? My suggestion is to break up the table, okay, or your values, into 2 very simple value categories. So here on the right side, we have what we call the boring side. And then on the left side, we have the exciting side. So yeah, so anyways, what I mean, okay, is when I talk about boring, what I mean is a carbon and hydrogens, and usually nothing else to make it too exciting in terms of highly electronegative groups. So basically in straight chain carbons, okay, we're likely to show up more as peaks leaning toward the right side of the diagram, okay? This is because there are, okay, no highly electronegative atoms to deprotonate the hydrogens to make them shift left, okay? We don't really have that going on here if you have more straight chain alkanes. Okay, so we're not yet. Okay, so anyway, so if you look at your halogens, for example, okay, the halogens will shift. They're a little bit more exciting than just a bunch of C's and H's. So they shift your values towards the left more, right? If you have aromatics or rings, they will be even more exciting, and because they have their own electric field, by the way. So that will then shift your ppm further left at around 7. And then finally, the hydrogens on a carboxylic acid or aldehyde are, you know, they're really next to such strong groups, okay? And then they will shift the, you know, the diagram way left, right? And last but not least, don't forget your reference point, the small peak here at 0 ppm, okay? That's your TMS. If you don't write it, but you have a peak showing up at 0, you still know it's just TMS, okay? It's just used to 0, or, you know, 0 value, 0 scale, more like 0 rise to 0, or create a basis reference for where the numbers will show up on the NMR graph, okay? Like I told you earlier, TMS is not a part of the molecule that you are analyzing. It's not in your sample, so don't worry about it. You see that little tiny peak at the very far right at 0, okay? All right, so that is, in a nutshell, your nuclear magnetic resonance spectroscopy. Now I'm going to go back to the animated PowerPoint and let's practice some problems. Alrighty, grade 12. This is, the last video was a little too long on Zoom, so I had to split this in 2 parts. Again, we are finishing, and this is the very, very last part of the NMR, nuclear magnetic resonance spectroscopy for identification of organic compounds in topic 11.3 in IB chemistry, standard and higher level. Right? Let's finish topic 11.3. All right, I think we're here. All right, finally, sorry. Here are the 5 questions I want you to work on. All right, so while we're looking on these diagrams here, we are not looking, okay, at like the values from your IB data booklet in table 27. Okay, all you're looking at is how many distinct peaks do you have? You are only looking at how many chemical environments are present. So what you need to be doing is, you got only 1 peak here on your NMR spectrum diagram, just 1 peak. So you only have 1 distinct group. I'm looking at the first one up here at the top. Okay, this hydrogen and this hydrogen, it's its own group. And then these hydrogens in the middle are their own group. So there would have to be 2 peaks. That's not it. Yeah? I'm looking at this one, an alcohol. Ethanol here. We looked at ethanol earlier already. Ethanol would have 3 distinct groups. There would be CH3 on this terminal end, this H is on this CH2 in the middle, and then the hydrogen that's isolated by itself that's attached to the OH group. That would be 3 distinct peaks, so it's definitely not that one. And we can look at the third one. These are CH3s here, and these are CH3 here. So these are very similar to each other. They might be on both ends, but they're both connected similarly to the same oxygen in the middle. So they're really just 1 chemical environment. There's only 1 peak, so it must be that one. Right? Next. Okay, now this one sometimes is used to throw you off. Be very careful. For a standard level, if you got like 2 peaks that are really close to each other, just count them as 1 peak. This might have accidentally come from a high resolution spectroscopy, okay? But actually let's treat it like it's just 1 peak, okay? So really we have 2 distinct peaks. Now, if I had the top one, I would have CH3 as 1 chemical environment, 1 peak. This, in the middle, I have 2 CH2s. But they're not the same. This would be 1 CH2 chemical environment, and this would be another CH2, because this CH2 is not the same as this CH2, because this CH2 is connected to a nitrogen, whereas this CH2 with carbon number 2 is attached to a very ordinary, boring CH3. So that's already 3 peaks right there. And then these hydrogens on the end of this molecule at the amine group, okay, these would be their own chemical environment as well. So then there would be 4 distinct peaks or this chemical environments here, and that's definitely not this one. Now we have to choose from these 2, all right? And this could be very tricky. Let me look at the bottom one here first. This would be 1 group here. This would be 1 group here. And they're very similarly attached and symmetrical, so they would be the same chemical environment. This hydrogen here would be another chemical environment. That would be a 2nd peak. Then the NH2s over here, they're both connected to the same nitrogen, so there would be their own peak. So that would be 1, 2, and 3 peaks right there. Now, with this one, look very carefully, even though it looks a little large and ugly. There are CH3 that are terminals. They're at the very end here, CH3, CH3, CH3. Got it? So they're very similarly connected. They are their own peak. And then you have these CHs in the middle, right here. There's the hydrogens of CH2 groups, but they're very similarly connected to the same central nitrogen. So they are a 2nd environment, a chemical environment. So really there are only 2 peaks here. So this is 3 peaks, this is 2 peaks. So I'm going to bet on this one if we're going to go with just 2 peaks here as a low resolution NMR diagram. Next. Okay, again, don't look at it as a high resolution, look at it as a low resolution. I'm going to probably count it as 3 distinct peaks, right? 1, 2, 3. Now, let's look at the top one. If it was this one, this would be 1 peak here. This would be another peak here. They would be very similar, very symmetrical. They're one chemical environment. And then there would be the hydrogen in the middle here connected to the carbon that had a Cl. And that would then be the second chemical environment. So then in this molecule, I would have only 2 peaks. Clearly, we have more than 2 peaks, so it's not that one. So now I got to pick from the middle and this third one. If I'm over here, I have this as one chemical environment, that's CH3 here. Then in here, I would have another chemical environment, these hydrogens of the CH2 here. And then you have this hydrogen that's connected to the carbon that has the halogens, the chlorines. So that would be the third chemical environment. So it's very possible that the middle one could be the correct choice. Let's look at the third one. I would have these hydrogens here that are the same chemical group or chemical environment. But then again, these hydrogens would also be, okay, so that would be, I guess it could be another hydrogen group, but they're very similar to this one. But then you can only really do one carbon at the same time. But then again, we did like this. So this could be just 1 peak, 2 peaks at the most. So it definitely cannot be this one. So we're going to go with the middle one because it has 3 distinct chemical environments, like 3 peaks here. There we go. Number 4, I have 2 main peaks. Okay, so cut out anything that has more than 2 peaks. This one over here, this is 1 peak, the CH3 here. This CH2 is another peak. This would be another one. The CH3 is over here that are connected to the carbon that has the double bond. So that's 3 distinct peaks, definitely not a match. So we're only looking at the middle and the end. Okay, so in the middle one, I've got then a CH3 over here and a CH3 over here that are terminal, but they seem to be very identical and symmetrical. So that's 1 chemical group. This one here, I would have these 2 hydrogens above the carbon, which is its own chemical environment. That's a second peak. And then we have these hydrogens here that are similar to each other that are both connected to the O's. So that would be a third peak. So I should have at least, if I'm picking the middle one, it would have been 3 peaks. So it's definitely not that one. And let's double check the last one. This would be 1 peak here. That this CH3 on both terminal ends, the terminators, they're very identical to each other. It's symmetrical. That would be 1 peak by itself. And then these H's belonging to the CH2 are both very similar to each other because they're both connected to the middle oxygen. So that would make it its own peak. So then there would be 2 distinct peaks here. So this looks like a match. Voila. And last but not least, we have this compound, which, okay, looks like only 1 peak, but you cannot ignore this one. This is actually a second peak, right? Now, so there's 2 distinct peaks. Let's look at this one. This CH3 would have its own peak right here. Good for it. And that hydrogen connected to the O, okay, would have its own peak as well. And being part of the acid would make it extremely electronegative, all the way really shifted to the left. So this is a strong possibility. Let's look at this ethanol. Here we go again with ethanol. We've seen this before. This would have CH3 as 1 peak, the H's on this CH2 as another peak, and a hydrogen attached to the O here at the end as a third peak. So definitely not this one, not ethanol. And over here, these are 2 terminal CH3s, both equally attached to the same O. So that's only really 1 peak, just 1 peak. So that would not be it, okay? So this is the only one that has 2 peaks. and it has a very electronegative hydrogen over here. So I'm going to pick the top one. Yay, we got it right. Okay, so that's done. All right, what a mouthful. Now, this is where, okay, standard level, just bear with me. We'll come back to more standard level problems in a minute. I just want to give a little preview to the HL students a little bit, what is coming in topic 21. When you guys get to topic 21, you'll be doing something similar to this with the NMR, but then again, you will see basically a little bit more details in the high resolution spectroscopy. Okay, you're seeing not just one big fat blobby mountain, you're going to see multiple jags coming out. Okay, so in these situations of the high resolution NMR, the area under peaks on these spectrums is proportional to the number of hydrogen atoms that causes a signal, because there's something called splitting that happens here. Here is your famous SNL again. So instead of just seeing like one big, just really singular peaks, you're going to see more on the high resolution NMR, these multiple broken up parts. Understand? And that's what we talked about earlier with integration. But this instead of having like an above integrated line above the peaks, the high resolution one will just show you in more resolution the split peaks in each chemical environment. Okay, so these are 3 chemical environments with the very distinct peaks. This is for topic 21, HL students. Okay, now this is still a little bit of a high HL, higher level topic. Okay, SL students, do not go away. You can fast forward through this part. I will get to some more practice SL problems in a little bit, but I just want to kind of squeeze this in from topic 21 a little bit for the HL students, okay? High resolution spectroscopy for NMR, all right? Again, like I just said earlier, they're not just single peaks. They are split into several closely grouped peaks, okay? Like this. So the magnetic field around each hydrogen atom is affected by small magnetic fields produced by neighboring hydrogen atoms. These fields can be either aligned or opposed to the external magnetic field. Again, take a look at that beautiful picture. There's your radio wave shot at it. Okay, nothing we haven't seen before. Now, as there is a 50-50 chance of each alignment, the same hydrogen atoms in different molecules may experience slightly different magnetic field strengths due to different alignments or differing alignments in the adjacent hydrogen atoms. Let's go back again and see this. There's the delta E again. So actually even SL students can learn this if you want. Okay, so this is called spin coupling and results in splitting of the peaks on the spectrum. So the multiple jagged pointy things coming out of each chemical environment. And the amount of splitting depends on the number of adjacent or nearby hydrogen atoms. That word adjacent, might be a little confusing for the HL students a little bit, but we'll get plenty of practice with that one, okay? Now, the number of peaks a group is split into, therefore, tells us about the number of hydrogen atoms attached to the carbon atoms next door to the group of interest. So that word adjacent we saw earlier is talking about the hydrogens that's attached to the carbon that's near your own hydrogen's carbon. And the number of peaks in a cluster is always one more than the number of hydrogens attached to the next door carbons. That is sort of an n+1 rule or n+1 formula. And this will mean absolutely nothing to you until you actually practice doing this. Got it? So bear with me, HL students. So for example, when I look at 1,1,2 trichloroethane, the 2 hydrogen atoms shown in blue are equivalent to each other. There is 1 hydrogen on the adjacent carbon. When I mean adjacent carbon, pause, god dang it. I'm talking about if this was the first hydrogen I'm looking at, the adjacent carbon is this one. This is the adjacent carbon. So I'll look at that hydrogen that belongs to that adjacent carbon. So then now the hydrogen shown in red, which we'll see in a minute, will have 2 hydrogen atoms on the adjacent carbon. So its signal is split into 3 2+1 peaks. That would make a triplet. So there's your triplet right there. Okay. Let's go back. Okay, so we're starting over here, n+1 mole. So example, in 1,1,2 trichloroethane, 2 hydrogen atoms shown in blue are equivalent, right? And there is 1 hydrogen on the adjacent atom. So the signal due to this hydrogen would be a doublet. Sorry, we skipped that a little bit. It's a little bit bad. Here's a doublet. So if I'm looking at this one, then this is a doublet I get because these hydrogens are both the same. It's this one plus the adjacent carbon. This is the next door neighbor carbon. Add its hydrogen to that carbon. So that hydrogen and then one of these equivalent hydrogens would make a doublet. That is how the splitting works here, okay, for this peak, for this chemical environment. And then now, if I'm looking at that one, if I'm looking from this perspective, count itself as 1 hydrogen, plus the 2 hydrogen that belongs to this carbon, that is the adjacent carbon to that carbon, and then there we get the split, the triplet, okay, the splitting of the peak into 3 little smaller peaks, okay? Okay, and then in this compound, 1,1-dichloroethane, so the hydrogen in green, okay, let's pause that sucker. The hydrogen in green has 3 hydrogens on the adjacent carbon, 1, 2, 3. This is the adjacent next door carbon. And so its signal is split into 3+1 peaks, or a total of 4 peaks. So you have to add these 3 on the adjacent carbon plus itself. That is a total of 4. And that's where we get these 4 here. 1, 2, 3, 4. That's a quartet. Okay. You see these all in topic 21, okay, in the NMR section of topic 21 in your IB data, sorry, not IB data bullet, the IB chemistry textbook on Cognitive website, okay, for HL students. So that's a little bit of a lesson here for spin coupling for HL students. And then I'm going to do a few, this is still one little section again on the HL spin coupling, and then we'll get back to doing both SL and HL. Understood? Okay, so what type of peak would you expect from the hydrogen shown in red? So this is a hydrogen. I won't count that one because that hydrogen is further away. It's blocked by the oxygen. So I'm going to look at this as a neighbor at the adjacent carbon. So this one would have 1, 2, 3, 4. Sorry, 1, 2, 3 from this adjacent carbon plus itself. That gives it a bunch. That would give 4 split peaks. So that would be a quartet. Okay, that's how it would be split. Understood? Voila. Next one. Now I'm looking at this hydrogen. This is ethanol, by the way, in case you don't remember. This is ethanol, and this is hydrogen at the end here. It's separated by the rest of this molecule by the oxygen in its way. So it has really no adjacent carbons to it. It's all alone by itself, so it's a singlet. Next, what would you expect from this hydrogen in the middle here? Okay, so it's symmetrical, so you could really go either way. So I could go this way, okay? So the adjacent carbon to this one is this one. 1, 2, 3, right? This is not a carbon, so we don't care. 1, 2, 3 plus itself, that would be 4. So it's a quartet. Okay? Next one. This hydrogen here. Okay? Its adjacent carbon is this one. But that adjacent carbon has no hydrogen. And these are all similar to each other. So it's just by itself, singlet. Next. What type of peak would you expect from the hydrogen shown in red here? So this is the group it's in. This is the next adjacent carbon, the nearby carbon, next door carbon. Itself, it has 2, plus itself here. So this adjacent carbon has 2 hydrogens already, plus itself in red, that gives it 3 So it will split into 3 different smaller peaks. That means it's a triplet. Next, what about this red hydrogen here? This is the group it's in. This is the adjacent carbon. This adjacent carbon has that hydrogen. Okay, but then this is another hydrogen here, but it's blocked by the oxygen, so we don't care about that. So we only look at this one plus itself. That will give it a doublet too. Next, what type of peak would you expect from the hydrogen shown in red? This one here, okay, is this group. This is the adjacent carbon. There is no hydrogen on it, so it's all by itself, singlet. Next, this hydrogen on the end of the molecule at the amine group. Remember, amine compounds are things that have nitrogen in them. If you forgot what the word amine, amine means, you better know it by now, students. That's all nitrogen-containing compounds when nitrogen is in a molecule attached to either carbon or hydrogen, okay? That's amine, A-M-I-N-E. Anyways, this hydrogen is blocked by nitrogen. This is equal to it. So it's too far away there. It's a singlet. Okay, that is higher level stuff from topic 21. Okay, so now this is sort of both of you again, because we do have these stuff. Even if these were not split into like these multiple peaks, you could treat them like, if you really zoom out, it would be like a low resolution spectroscopy, correct? So then you could really look at it like that way, and then they would all be, you know, low resolution NMR. This is, okay, pretend like it's a low resolution NMR, but these are values that you would be getting. These are a little bit off, by the way, from your IB data booklet in table 27, okay? But then you could really look and see which range you're in, and then look accordingly to the ppm values here, okay? Okay, so here is some 5 questions that both SL, standard level, come back. Don't leave me. Don't leave this video yet. Sorry I had to, you know, kind of interrupt this video with some HL stuff in the middle. But now we're back to topic 11.3, standard level and higher level. Now these are back to single peaks again. This time it's based, you know, we're really not just going to be looking at only, you know, like sort of how many peaks, how many chemical environments do I have, okay? Because we don't have that kind of question here. I'm trying to identify that, like, whatever highlighted hydrogen I have, which peak do you think it is referring to on your ppm scale from 0 to 12? So with what I've shown you earlier in the other part of our video on NMR, you should be able to do this now. And yes, you could look at your data values, okay, from your IB data booklet, but technically you can avoid it if you can. Because why? We're going to use common sense here, okay? So I've got peak A versus peak B, and where? So if I'm really one of these hydrogens, the terminal hydrogens that are the boring side of my scale here, it would be more to the right. This is electronegative. This is a hydrogen connected to the more electronegative part of the molecule. So most likely this hydrogen is going to be the one on the left, okay? More shifted to the left. So we don't even have to use the data booklet. We could just say that that's probably peak A. Okay, next question. All right, now we're looking at the terminal, the terminator hydrogens at the end of the molecule on both ends. They're equal to each other, right? They're both just H's part of a CH3 that ends the molecule. So that will always be more to the right, closer to 0 ppm. Right? So these are the boring hydrogens, so it will be peak B. You don't even need your data booklet. Next. Okay, so be careful here. 2 peaks here. This would be the more boring hydrogen, right? That would have to be like the terminal hydrogen on that side. These hydrogens are connected to a carbon that is connected to the more electronegative chlorine. So most likely these hydrogens are going to be the more electronegative shifted left peak. So it's peak A. Okay, and now here again, we've seen this one before, sort of. Last time we had a OH, now it's just an H. So here we have, if we had the terminal carbons that are boring carbons, that would be at peak C. Okay. This hydrogen is attached to, okay, the carbon that is connected to the double bond O. So in this case, could be peak A or peak B. You mean? So, but we might need a little help from the data booklet here, from this data booklet, from the A-level chemistry. So if I'm looking at this one, all right, so I have, let's see, this is the hydrogen that looks like what we have here. It should be ppm, I'm sorry, around 9 to 10. This is too low, so it's probably around here. So I'm going to assume from the data booklet, it's around peak A. Okay, so that one, we do need to use a data booklet a little bit to help us. Okay, now we got, oh my God, 4 different peaks. All right, so we have a boring CH3 part here. That would be peak D, so that's definitely not it. The CH2 is a little bit less boring, but a little bit still boring. So that could be peak maybe C, perhaps, who knows. But then you've got peak A and B. So I'm assuming that this H on the terminal OH is going to be peak A or peak B, right? So this one, I could probably judge it based on the number of divisions. This is where you can apply the HL more. That hydrogen is really not going to be split into so many different parts. So I'm probably going to estimate it as peak B. But if you're not really sure, you can look at your data booklet and look at the H's on the end of an OH, right? So what I'm looking at is like this one. That, no, not really, that's too high. That would be way up here. So we don't have anything up here, okay? So we really have only like this one. Oh, this is the odd one. That could be anywhere between like 1 to 5 ppm, right? So really, the only thing that could really help you is you might need to use, so this is why standard level, you might need to use that sometimes because they might throw you a question like this, that if you knew a little bit the higher level splitting of the peaks, that could really help you with this. And it only really has just one, because this would have more splitting, right? So this one, right, would have to be the one that is, you know, just one peak. So I think it's peak B. Yes, all right, good. That is basically, yeah, enough practice for you. But anyways, application, NMR spectroscopy could use the same technology as magnetic resonance imaging. It's an important non-invasive method of getting information about what's going on in your body. This is for the doctor wannabes, okay, about internal structures in your body used in diagnostic medicine and scientific research. So basically NMR is used in the pharmaceutical industry to check the purity of compounds. That's why I said it was very important earlier. If you're going to go into medicine, whether it's pharmaceutical, medical technician, or be a doctor. And now what you see in the higher level topics later, topic 21, is there are some problems that actually need to combine what you learn on the mass spectrometry combined with infrared spectroscopy, the IR, and combined with NMR for more challenging problems if you really want to identify what organic molecule you have, okay? That's all in topic 21. All right, so we are done, you guys, with the NMR spectroscopy from topic 11.3. Okay, I hope this video has been helpful to you. And so we are done, standard level. Standard level, you are done with all the topics now because you've now finished topic 11. The remaining topics of this school year is topic 20 and topic 21. Okay, so that will only be for higher level students, right? Now, mind you, Ajahn Rick Spadafora and Ajahn Jeff has mentioned in the email that there's a strong possibility that the IB exams for our school, Prem, might be canceled. Maybe all of Thailand might be canceled due to the recent outbreak of the coronavirus that has gotten more serious, especially in Chiang Mai here. So we will probably find out very soon if we're even going to have these exams, okay? And if we don't, that means that, you know, your internal assessment, IA, might be the only thing you get for a grade. So good luck to you if you did a bad job. So, but anyways, that is it for standard level topics. And in the next videos, we will go back to topic 20 to higher level, organic chem. Actually, I'll do that last. I want to finish off topic 11.3. Sorry, no, topic 21 for the HL students, because now that you've done topic 11.3, we can quickly finish topic 21, which is the higher level spectroscopy stuff, you know, for topic 21. And then we will just end the entire school year for HL students with topic 20, which is going to be definitely the most difficult chapter you've probably seen. And that's why I save the best for last. All right, anyway, so I will see you guys later, HL students. SL students, well, Tracy, you're the only one who's not giving me your IA. Girl, you better get that report in, or I'm gonna only submit your not so good, okay, temporary draft. Don't make me do that. So get that in on Manage Back ASAP now, today. Goodbye, you guys. See you next time.